if R is Dedekind with quotient field K, and F is a finite extension of K, F is of course field, then T, the integral closure of R in F is also Dedekind. So the situation here is R has some quotient field K, go up finite degree extension here, and you take the integral closure of R in F. Its quotient field is in fact F as well, and this is actually Dedekind. There was a similar theorem that we had for proof domains. Let me kind of sketch out. Since R proofer, we know T proof without finiteness hypothesis. So that's a previous result. We already know that that's second proofer, even without the finiteness. So our burden is to show that T is also Noetherian. Because if T is Noetherian and it's proofer, that means that, well, proofer means every finitely generated ideal is convertible. And if it's Noetherian also, that means every non-zero ideal is convertible. So that's our burden here. And we're going to need all our hypotheses because actually we need that R is Dedekind, so it's Noetherian. And we need the finiteness. I didn't have to use either of those assumptions for what I've got so far. But now I'm going to go back to the fact that R is Dedekind. Yeah, Noetherian. So I'm going to have to use that. I'm also going to use the finiteness of the extension here. So let U1 up to UN be a basis for the field F over K. Of course, F is a finite extension, which one of the equivalent ways you can think of that is it's a finite dimensional vector space over K. So there's the basis here. We assume, without loss of generality, that each UI is in fact in T, right? Because actually these are fractions bones in T, and so you just clear the denominators if you like, and it make it no difference. So let T0 be let T0 be this ring. So I'm going to take these basis elements, all of which are in T. I'm going to throw them into R. I claim that T0 is theory. Right. Know why? I've got another kind of Noetherian puzzle coming up later, and I'm not going to tell you that. It's a more connection for homework. Why is T0 Noetherian? Well, we point out R is Noetherian in the first place, right? So is R in polynomial variables. This is the Hilbert basis theorem applied n times, right? And there's also this homomorphism, right? Basically plugging in each UI. This is clearly onto in the homomorphic image of a Noetherian ring is a Noetherian ring. Let me give you a quick proof of that. Homomorphic image is R mod I, right? If every ideal in R is finitely generated, then every ideal in R mod I is finitely generated because the ideals in R mod I are one-to-one corresponding to the ideals of R that contain I. And so all you need to do is use the original generators. You can even throw out any generators that are already in I. Everybody okay with that? Okay, so T naught, this animal here is Noetherian. And let's see. And it's also one-dimensional. That one might be one-dimensional. Why is it one-dimensional? Well, let me build a little ladder. What's true about each of these extensions? I'm sorry? Oh, well, no, what's true about the extension? So, what properties do each of these extensions have? Can you kind of integrate it into your circuits? That's right. They're all integral extensions, right? Because all the U's are integral over R, right? So what's in here? This is just a linear combination of powers of UI. These are all integrals. So this is an integral extension. U2 is integral over R, so it's certainly integral over this integral. So all of these are integral extensions of R, right? So P naught is integral over R. Therefore, then P naught is then P1 of R. Okay, so that was useful. There's an application of our earlier theorem about integral extensions of observed dimension. So what do we got here? We got it's Noetherian, and we got that it's one-dimensional. Note also that T is the interval closure of P naught. Right? Certainly, T is integral over R. So T is integral over T naught. Right? So And why is that? Yeah, well, that's because there are no extra integral elements, right? Integral is transitive. And so, in particular, P is the integral closure of T naught, which is a one-dimensional Noetherian domain. So in conclusion, P is itself, or T is integrally closed, because integral closures are integrally closed, and is one-dimensional and because we had that result last time that we haven't proved yet that we're going to prove that any overringing of a one-dimensional Noetherian domain is again one-dimensional Noetherian. So as promised in the figure, because it's integrally closed one-dimensional Noetherian. Okay, any questions so far? Okay, so we're now going to take off down a road that will eventually bring us to a proof of this statement that if you have an integrally closed, if you have a one-dimensional Noetherian domain, then any overring is also one-dimensional Noetherian. But first, let me make a remark about modules here. This is a chain of R modules. Yeah. M So if any successive pair of modules, if this quotient is simple, and remember what that means is there are no non-trivial submodules of this, or no non-trivial submodules, MI mod MI plus 1. If MI is simple, that means in a certain sense these modules are as close together as you can get without them being equal. Loosely speaking, then this is called a composition. Which is a terminology that I object to. That really should be a composition sequence, shouldn't it? If you have, if M has a composition series, then any series can be refined to a composition series. And if you have two refined series of a module M, then they have the same length. Let me, after that reminder, let me give you the following theorem here. Actually, throw in another definition first. Does anybody know? Okay, everybody's familiar with Ethereum because you run across that path. Does anybody know what it means for a ring to be Artinian? Anybody recall the definition of it? Right. Okay, so let me give you that formula. We say R is Artinian. You know, given a descending, and by the way, I'm going to put this in terms of ideals, but this could be recouched in terms of modules as well. If given any descending chain of ideals R, let's say then there exists a international numbers such that I to the n plus k equals ik for all n and numbers. So in other words, you can't go down forever, you eventually must stabilize, right? So this is like sort of a dual notion from the theory, right? Instead of ascending, we're looking at descending, right? By the way, does Noetherian imply Artinian? Does Artinian imply Noetherian, or are they independent? And of course, can anybody think of an Artinian ring that isn't a field? Well, there's one silly thing that you can do, right? I mean, if your ring only has finitely many ideals to begin with, then you have to satisfy the descending chain condition, right? So certainly any finite ring is Artinian, right? Can anybody name a ring that's not Artinian? For example, Z, right? Look at the ideal generated by 2, 4, 8, 16, etc., etc. This decreases forever with no stabilization, right? Notice Z is Noetherian, but not Artinian. But is it true? I mean, it's really kind of weird, isn't it, about the order of the ideals? Does the ascending chain imply the descending chain? Well, obviously not, because Z has the ascending chain condition, but not the descending chain. This is descending imply the ascending. The answer is yes. In fact, Artinian is much stronger than Noetherian. So here's kind of a fun question for you. Artinian actually implies Noetherian, right? Anything that's got descending chain has the ascending chain. Descending chain is a much stronger condition for all ring. Does anybody know what it takes to make this equivalent? So that is to say, Artinian implies Noetherian. Noetherian and what other condition is equivalent to Artinian? This theorem really rather interesting. I'm going to give this to you without proof. Maybe we'll come back to it later. R is Noetherian, or I'm sorry, R is not Artinian. That is, it has the descending chain condition. If and only if R is Noetherian, and a dimension of R is a zero. So that is certainly a strong condition. So not only do you have to have the ascending chain condition, but it also has to be true that all prime ideals are maximal, right? So the Noetherian rings exist in all dimensions, and including infinite dimensional. So the Artinian rings are precisely the Noetherian rings. They're squished flat in the sense that all their prime ideals are in fact maximal. Okay, so let me give you the following theorem. Now, make sure that you know what Artinian means, at least. 526. And this will be as a part of this theorem, as a matter of fact. Let R be commutative of 1. The following are equivalent. 1, R is Noetherian and 0 dimensional. Number 2, any finitely generated R module has finite length. And here I'm referring to like the length of the composition series. R has finite length, that's an R module. And number 4, R is Artinian. That it has the descending chain condition. Okay, so I'm going to go through part of this at least. Let's do 1 implies 2. There's going to be a key factor we need that I'm going to ask you in your homework along the way here. Proof. So let me note, as R is 0 dimensional, all the primes are prime ideals are both minimal and maximal. Since all prime ideals are maximal, they're also minimal as well. As R is Noetherian, each ideal I in R is contained in only finitely many primes. Well, I'm not saying this quite right. Let me rephrase it this way. As R is Noetherian, each ideal I in R has only finitely many primes. Minimal over. And what I mean by that is, I think I've mentioned this before, but let's just make sure. We say P is minimal over I. If P is a prime ideal that contains I, and there is no other prime Q such that that's what I mean by minimal over it. It's sort of the smallest prime that contains I. Now, this statement might not be completely clear, and I want you to prove that later. So it turns out that if you have a Noetherian ring, this is one of the consequences of Noetherianism. If you have an ideal, look at all the primes that are minimal over it, right? There's only finite many of those guys. Right? Let me point out that you might say, oh, but Jim, if you look at the element X, this is contained in, well, let me make this an infinite field. Just to make it easier. Aren't there infinitely many prime ideals containing this ideal here? Right? And the answer is yes, but let me point out that X itself is prime. And the only minimal prime containing X is X itself, right? So it's only containing one ideal, it's minimal. Right? So that doesn't say that every ideal is contained. In fact, it may be contained infinitely many ideals, but only finite can be minimal over. As a corollary to this, let me point out, if I walk up to you on the street and give you an ideal, what is the radical of this ideal? It's the intersection of all primes that contain it, correct? If you're in a Noetherian ring, that means its radical is an intersection of finitely many prime ideals, right? Because every ideal is only containing finitely many primes minimal over it. So this is something that this isn't hard to prove, but it's something that's probably not immediately obvious. So, given the statement, there exists only finitely many maximal ideals. Remember, we're in a zero-dimensional ring. M1, M2, and N containing 0. But remember, 0 itself is an ideal, right? And this ring is Noetherian and zero-dimensional, but that means that 0 is contained in only finitely many primes, and that means that there are only finitely many primes there in the first place. So, note look at the product of this assortment of maximal ideals. This is contained in the middle radical. Well, this is contained in the intersection of MI. Middle radical. Everybody agree with me? So in other words, what that means is everything in this ideal that is the product of these ideals is in fact a nilpotent element. And ours is an Noetherian ring, which means this ideal is finitely generated. And so, the ideal M1, M2, Mn is contained in the middle radical R and is finitely generated. So the ideal itself is nilpotent. This is not always true nil radical, but however, since it's finitely generated, the ideal itself is nilpotent, which is actually stronger than saying that it's full of nilpotents. It means the whole ideal itself is nilpotent, and it means that, so we're going to find a K. So there exists, let's say, a minimal K in the natural numbers, such that this is the zero ideal. Now that I've gathered this up, remember what we're trying to do. We're trying to show that any finitely generated R module has finite length. So let N be a finitely generated R module. Now I'm going to make this. I'm going to build this chain between 0 and N. I can put all kinds of stuff in between there. You know, 0 via right. So if I have some intermediate module B that's a submodule then containing 0, then of course I can always build a smaller module MIB, right? Just by I think that roach bullshit. Anyway, so if I've got an intermediate B between N and 0, then certainly I can also insert MIB, which may be smaller. If I've got equality, then you know I can absorb that in there too. And of course, I can also do things like so I can build chains of modules this way. Notice that B mod MIB is finitely generated over R mod MI. And of course, MI is the maximal ideal of R, so that's a field. And so, since this is a finitely generated module over field, it's a vector space, which means there are only finitely many modules that can be inserted between B and MI. And so that's exactly what we need, because what we've shown is that if we build any chain of ideals like this, then given any gap between B and MIB, there's only finitely many to go in there. So every finitely generated module must have finite length. 2 implies 3. I don't think it's too much of a headache, because if you recall, the statement in 2 is any finitely generated R module has finite length, and 3 is any R has finite length as an R module, right? And so actually 3 is kind of a special case of 2. So 2 implies 3 is not an issue. 3 implies 1. How about this one? So what we want to do now is R has finite length as an R module. We want to show that it's 0-dimensional and Noetherian. If R has finite length, then it certainly must satisfy the ascending chain condition. Because actually, of course, ideals are R modules. The ascending chain condition. And so our theorem we want to show, of course, that R is 0-dimensional, and that's what burden here. Zero-dimensional, that is. So let's suppose that we have a chain of primes. Of course, we want to show that this can't happen. There can't be a chain of 2 comparable, distinct prime ideals. Then pass to R mod P, which is an integral domain. So mod out by this bottom prime pass to R mod P. And then use the notation by assuming R is the domain. So we assume that R has finite length, pass to R mod P, which is now an integral domain. Assume that we've got a chain of 2 primes like this, pass to R mod P, it's now a domain. So now start over again by redefining R mod P as R. So we use that terrible notation. And it suffices to show that if R is a domain of finite length, then R is a field. R is a domain of finite length. Then R is. Now, to this end, since R is a finite length, we find a minimal non-zero ideal Since R is a finite length, that means that if you start at R and you look at the chain of submodules, it's got a finite length down to 0. So there must be an ideal, a minimal ideal over 0. Not 0 ideal I in R. Notice that, of course, let's say so the reason this exists is R is a finite length, right? And so this fixed finite length, and so this ideal right here, I, there must be a minimal one, minimal non-zero ideal, because if not, then this chain can be expanded. And if you can keep going, then it doesn't have finite length anymore, right? So there must be some non-zero ideal of minimal length. Pick some element. Select a non-zero X in I. And notice that that's equal I, right? And the reason for this is it's certainly the case that Xi is contained in I, right? That's got to be the case. And it's got to contain 0, right? And in fact, this one is strict because of the fact that R is a domain, right? Because otherwise, the only way that X comes out to be 0 is if X kills everything in I, but this thing's a domain, so that's impossible, right? So since this is a strict, then this has to be an equality. Otherwise, I can insert Xi in here, right? And then that contradicts the fact that I is minimal non-zero. So that's a typo there. So there exists an alpha in I such that right? X alpha equal to X. Thank you. X alpha equals, thank you. Yeah, and X is not 0. And it's in I, and that's how we know that's there. So X times alpha minus 1 is equal to 0, right? Well, X is not 0, and R is a domain. So alpha minus 1 equals 0, and so alpha equals 1. Right? Therefore, 1 is in I. 1 is in I. So I equals R is minimal. Right? So R is equal. Because remember, I is a minimal ideal. So what you're saying is the whole ring is a minimal non-zero ideal. That means the only proper ideal in the ring is 0, and so R is right. We make one more remark here. Notice that 3 and 4 are equivalent, because if R has finite length as an R module, then that means it has to satisfy the descending chain condition. And on the other hand, if R satisfies the descending chain condition, it can be pretty easily shown that R has finite length as an R module. So that kind of ties it together mostly. Let me give you a quick corollary before we break for the day. Let R be a domain. R is Noetherian, and dimension, let's say 1. If and only if, for any non-zero ideal in R, R mod I has finite length. Okay, any questions on that? See if you can see how this connects. It connects pretty easily to the previous one. And think about that question, because I'm going to ask you that later. Why is it true that in a Noetherian ring, every ideal is contained in only finite many times minimal of? Okay, questions? All right, well, you all have a good one, and we will see you. Oh, Alice Swede will be talking this week. She's a new lecturer in our department. So very excited about all kinds of things. So, and I think she's going to give a great math club talk about doing designs. There's going to be some algebra, number theory, all kinds of stuff in it. So I encourage you all to be there. Other than that, we will see you on Friday.